we're just going to do an example. This is a popular lithium iron phosphate battery, which is generally going to be twice as expensive, and we'll see what the performance is like. This battery is rated, if you use it per the manufacturer's recommendations, they'll give you a 10,000 cycle rating, provided that the depth of discharge is 80%. And it's kind of funny because lithium-ion batteries are portrayed as being more elastic than lead acid, more responsive, more efficient, etc. Efficiency in a solar battery is not the most important design criteria, especially with a solar thermal peaker or solar peaker. The energy involved is not very costly. It's the savings that are incredibly valuable. And so we don't really care too much about efficiency, but we do, want our battery to last as long as it can. So, all I'm trying to say is that, even lithium ion has its limitations in terms of dischargeability, and there's even, higher quality chemistries that we'll get into that are more favorable for things like rapid discharge. However, it's rare to have a facility that only has a maximum spiky load for 15 minutes. Usually a maximum load might run for an hour, and you would want a 2-hour battery in order to make sure that under worst case scenario, you can still level that load. And so, if you have a 2-hour battery and you run it for an hour, it's only going to be discharged by 50%. This lithium iron phosphate company says we'll give you a 10,000 cycle rating if your depth of discharge is no greater than 80%. So we're gonna take a peek at Tesla's warranty on the Powerwall 2. And so here's the Tesla Powerwall 2. It's a 13.5 kilowatt hour battery, and the warranty is either 10 years unlimited, and that's if it's just kind of sitting there not doing anything. But the real warranty is a 10-year warranty for 37.8 megawatt hours. So how do we get to comparing this 80% depth of discharge, 10,000 cycle warranty to comparing against Tesla? Well, we have a battery that's 13.5 kilowatt hours large, and we got 37.8 megawatts of output. And so all we need to do is take our calculator out and say, okay, our battery is 13.5 kilowatt hours, but we want to limit it to a 80% depth of discharge cycle. And so our battery is effectively 10.8 kilowatt hours. So we do 37,000 kilowatt hours divided by 10.8 kilowatt hours, and that's 3,500 cycles at an 80% depth of discharge for the Tesla Powerwall. So when you compare that against lithium iron phosphate, the next step up, you're getting 50% more bang for your buck, provided that you can come up with the capital to do that, because there still is a very real limitation of how much these battery systems can cost at the commercial level. And so the way that I would look at it is, if you feel like you can achieve a payback on the Tesla Powerwall at 3,500 cycles, because when you look at 3,500 cycles, you say, okay, well, what does that actually mean? If it were cycling every single day of the year, that would be a 10-year battery. And a solar peaker is not going to last, is not going to cycle every single day of the year. And so even if it only cycled for half that, every other day would still be pretty extreme. And so what I'm trying to say is the Tesla Powerwall is still going to be a very valid solution for a solar peaker in terms of the lowest capex expenditure for a kind of consumer off-the-shelf product that you can, that would fit a small, under $1 million solar peaker project. Go and grab the Tesla Powerwall, and it's a good selection. But if you aren't so budget constrained, the next step up is lithium iron phosphate, and it's more cost effective in the sense that the battery is going to last a lot longer, but there's also the cost of capital involved. What that also means is that maybe lithium iron phosphate is a better choice when in areas where the cost of energy is high, to get a higher quality battery that'll last longer, that's more versatile. To some extent, we are subject to changing electric policies. And so maybe the commercial solar peaker model only works really well for 10 years, and then they change the rate structures to make it, not as viable. And so maybe in that case, you just get around to eventually taking the building off grid if possible. And so in short, the lithium iron phosphate is just kind of the next step up in terms of quality. Now, there's another thing that we on this spec sheet to look at, which is the C/2 rating. Yesterday in class, I was calling it a C2 rating, and there was a comment, and they were like, oh, C2 and C/2 are very different things. And I want to explain that comment. When we talk about a C/2 battery rating, what we're talking about is this is the battery performance and amperage and warranty and everything on the spec sheet is assuming that you're discharging this battery over a 2-hour time frame. And they don't really, Tesla is taking the Macintosh approach of not even allowing you to discharge their battery faster than that, because they give you a 13.5 kilowatt hour battery and they only put it on a 5 kilowatt inverter. So, if you have a 13.5 kilowatt hour and you put it on 5 kilowatts, it's gonna take you, about over 2.5 hours to fully discharge that Tesla Powerwall. They're using the hardware to constrain you to a maximum discharge rate of a C/2, so that you stay within their warranty period, and they can give you a nice long warranty, but also not let you kind of supercharge the battery and use it really heavily. And some of that would be by discharging the lithium-ion batteries too fast. It becomes a fire safety issue, particularly because when the battery does catch on fire, it's very difficult to put out. So C/2 is discharging the batteries over a 2-hour period, whereas 2C is discharging the batteries over 30 minutes. So they're very different things. The Tesla Powerwall does not allow you to have a 2C discharge rate for the battery. It confines you to C/2, in part because it is a low-end lithium-ion technology, and being low-end, it's also low cost, which has its advantages too. They're trying to make lithium-ion batteries for the masses. Lithium titanate is, let me get the presentation back up. Is a a step well beyond, and there's one in the middle. We kind of leapfrogged over another technology, but lithium titanate is like the unicorn that people are that's starting to come out of Chinese battery manufacturers. You can get pricing for it. It's very expensive, but this is considered kind of the top shelf of lithium ion, and it's rated for 30,000 cycles instead of 10,000. So it's 10 times as good as entry level lithium ion. It's just very expensive if you can actually buy it with murky supply chains at this point. It's a very immature industry. In fact, there's another technology called a supercapacitor that has very similar performance to lithium titanate, and there's only one supercapacitor company that I'm aware of, and some solar installers are dubious that they're not actually making a supercapacitor, but they're actually making a lithium titanate battery because they have very similar specs. Let's see. Some technical specs. What's kind of interesting is weight in lead acid is a measure of quality. A top shelf lead acid battery, it has completely different performance than a bottom shelf low acid battery. A top shelf lead acid battery is very similar in performance to the Tesla Powerwall. They're closer together than the range between bottom shelf lead acid and top shelf lead acid. It's just even with a top shelf lead acid, you can't discharge it at a C/2 rate. Top shelf lead acid is generally rated for a C/6 rate. As in, we're not even going to tell you the specs for less than C/6 because the battery will stop working if you discharge it any faster than that. What we see with lithium titanate, is that it weighs more per kilowatt hour of storage. So that's kind of interesting. That adage of value is measured by weight is kind of true in the battery industry. Let's see. These are just some links to. I linked here the supercapacitor company. They make a energy server, which is kind of interesting. That's where you could plug in multiple. I'll put the link in the chat box if you want to look at them. Normally, I don't like mentioning brand names in class, but whenever the company is doing something particularly unique, it's kind of unavoidable to how to reference them. But they're doing supercapacitors, and if you look at the spec sheets, they're saying they're substantially, high performance, and what they say they use is the tips of their supercapacitors are coated in lithium titanate. It's just something that is very good at conducting electricity with very little degradation. And so what you can see, and to kind of bring the conversation home, you can see that they're saying they can get a maximum charge and discharge rate of almost 2C, which is 30-minute, in this case it might be 45-minute discharge rate with as many cycles as you possibly want. Of course, something like that would be exorbitantly expensive. And the applications that they say is you put a little small one alongside any kind of storage technology in order to kind of smooth out the hysteresis of your electrical load, so that it can help lower performing batteries with surge loads and things like that, which I think is pretty interesting. And that's where they get into the concept of you need an energy server to tell which batteries to turn on at which times so that you can actually combine a wide range of storage technologies on a single job site. In our off-grid class, we kind of talk about how you could have a lead-acid battery providing base load, and then have a lithium-ion battery like the Tesla Powerwall operating in a demand management mode to create kind of a simple energy server where the lithium-ion battery turns on only when the building demand surges above a certain level, which is hard-coded. We talked about that yesterday, and then whatever is wired in parallel to it with base load, it doesn't really matter. What this chart is showing is that there's a range of storage mediums. We see here in this big block we have lithium ion, and as compared to top shelf lead acid, the difference is you can charge and discharge it more rapidly. It has a larger range to it. What's also kind of interesting is lithium ion comes in higher voltages, and so at some point the lower voltage lead acid starts to limit you with the raw amount of power that can come out of the battery. You reach an upper limit with a lower voltage, regardless of your technologies. So lithium ion is generally done at a higher voltage, which is also better fitting for commercial job sites that are running at 480 volt electrical service. Might as well have a battery that's up at that voltage as well. Whereas supercapacitors or mechanical flywheels can be discharged much more quickly in a matter of seconds. I have a cousin who's a elevator technician, and he says they use flywheels and elevators because the elevator is going up and down the building in a matter of seconds, and they want to capture that energy in the flywheel. That type of electricity storage is better with capacitors and flywheels than even with lithium ion. Now, I do still see movement and discussion of flow batteries. Flow batteries are very long cycle batteries, but we can see they're not high performance batteries. And so, when you hear about flow batteries, which are just different battery chemistries, flow batteries are generally being geared towards utility base load. If it's like a 12-hour load, that powering it with a large flow battery is considered to be cost effective compared to running base load with lithium ion. I don't know too much about flow batteries. To me, they still seem to be more in the research and development phase. Now, when I say the batteries are limited to like C/2, a 2-hour discharge rate, that still doesn't mean they can't have some surge capacity. So the Tesla Powerwall, in its specs, it says it can surge up to a 1.4 C for 20 seconds. If it stayed any longer than that, it would start to overheat. My off-grid battery inverter is a 12 kilowatt battery inverter, but it can actually output 36 kilowatts for about 30 seconds. And so when you are surging a load like that, it's nice to have a battery that also has similar ratings, because if you had a battery with worse ratings than that, then that would lead to degradation of the battery. What we're doing on this off-grid home is taking small loads, like right next to me there's a dehumidifier that is always on. and we're killing it whenever the basement or whenever the top floor goes through a surge, and as well as stopping ceiling fans and things like that to kind of give us a flatter load profile. And we see that lithium iron phosphate can handle an even higher rate of discharge for 10 minutes rather than 20 seconds. And so, what this is saying is that if you have a particularly spiky load that you don't need a 2-hour battery for, lithium iron phosphate might be a better choice. We see a higher price point, but also higher performance specs. In other words, you get what you pay for. Whereas lithium titanate can handle a 1.C continuous rating purportedly. There aren't any lithium titanate commercial buildings, to my knowledge, in the market. I get ads for lithium titanate batteries from Chinese distributors on LinkedIn, and that's about all that I really see of applications of lithium titanate in the wild, other than talking about its use in supercapacitors. But this is kind of a range of pricing just for the cell. The smallest unit of the battery, not the pack, which is the casing that the batteries go in, or the battery management system, or anything like that. This is just raw cell estimated pricing from from very murky supply chains. All right, so if the battery might be coming through a murky supply chain, that's where the brand name companies come in for commercial applications to say, no, we're buying a lot of these batteries and we're sending our representatives to the battery facilities to make sure we get the good stuff and not the bad stuff. And so your power electronics companies are getting into that. They're saying, if we're buying these batteries from these original equipment manufacturers and putting our name on them, we're going to want to sell you the hardware that controls how the battery is used so that we can actually support the project, because otherwise we don't have any control over how you go and use your battery. So these are products made by Delta. They have a power conditioning system, which is their 125 kilowatt inverter, that it says schedulable demand. So we saw that yesterday when I'm changing all the kilowatt levels. That's a schedulable demand where you can put in the date range or hours of the day and tell it what level to do load management at. Then it says or PQ control, which is a little bit more intelligent, based on the storage capacity in the battery and the load profile data. It can do a more intelligent guess and keep your demand below lower your demand perhaps even more than what you programmed it to be. So there's a lot of companies that are touting PQ controls, and I don't think that that's very well established yet. I think that it's a good thing for companies like Delta to offer more intelligent algorithms to lower your demand further. For instance, if you are halfway through the month and you've never gotten anywhere, close to fully draining your battery on a demand management setting, then you would want the battery to take the highest demand for the entire month already achieved and load level at that lower, threshold. So, and again, that could also be predictable on weather. It's like, okay, well, if it's not going to be the hottest day of the month and we've already had hotter days, then, maybe not run the battery so hard. Um, So what does PQ stand for? It's a engineering term that's basically a like a force feedback control circuit. So we would use PQ circuit feedback for balancing a robot. So if you built a robot on wheels with a long stick on top that balances a plate on top of the stick, based on how off balance the stick is, the robot works a little bit harder to scoot underneath it and catch it. And so that's a little bit more elegant for how you ramp up or ramp down the battery discharge rate, as opposed to kind of, guessing what the load will be, or assuming that every single time the building gets up to a certain level, you gotta, hard slam the battery on, rather than throttling it back for additional demand down the road. So I guess what I, I don't know, if you imagine a surfer out in the ocean looking at the waves coming in, some waves are going to be larger than the others. And so the surfer may not want to go catch, the lower wave. He might want to just wait for the higher wave to come on. And if you can more intelligently determine, what a good wave to load level is, that's the realm of PQ controls. I'm not sure the P and Q actually stand for anything. I think they're mathematical symbols. For one is the primary, feedback, and then the Q is the secondary feedback. As far as industry terms go, battery module is the real interesting one. It's also referred to as a battery pack. But the technical term is the battery module. In the solar industry, National Electric Code refers to a grouping of solar cells as not solar panels, but instead solar modules. Similarly, a grouping of battery cells is called the battery module. So you can get low voltage battery modules, and inside the battery module is a grouping of 3.3 volt lithium ion cells, and that can go up to 48 volts or even as high as 300 volts or 1,000 volts, or kind of custom to your application. And so you would get a grouping of battery modules that are stackable to build up to as high a voltage as you want to go. So for instance, if you're doing a utility scale solar farm and everything's up at 1,500 volts, then you might want a 1,000 volt battery to go next to it. But if your facility is only at 208 three-phase, then you may want a battery voltage that's closer to 208 volts, because when you match voltages, the whole energy conversion process gets more efficient. It's rather inefficient to go from a 600 volt solar array down to a 48 volt battery bank and back up to 120, 240 split phase. And that's really where you see efficiency come in with lithium ion, is that it's done at a higher voltage. But then again, you just have to go with me on this one. Efficiency doesn't really matter for solar peakers. The energy doesn't matter. It's all about that instantaneous discharge. And likewise, in an off-grid system, efficiency doesn't really matter, because you should be generating an overabundance of energy when you're living off-grid. You should never have an energy shortage, so you should have some energy to spare for inefficiency. Um, when you're at a utility scale power plant, um, and you're trying to do a base load battery system for powering the grid, not just at peak times, but also off peak times, then efficiency would be a little bit more important. So these battery modules stack into a cabinet, and every battery module has what's called a battery management system, which will tell the battery modules, when to turn on and monitor the voltage across the cells, to help it, discharge the battery bank appropriately. And then these things just kind of ramp up to as large as you want to go. A small solar battery might just be one server cabinet big. A large one might fit in a shipping container next to the building. And I really like having the batteries detached from the building if you have the space. It just gives you a little bit more, security in the back of your mind. Nothing's going to go wrong for the long haul. And so here are just some specs. One cabinet of lithium-ion batteries can hold about 40 to 50 kilowatt hours of lithium-ion storage. Now, one thing that is interesting to me with Delta System is they're using a lithium-ion technology that is not low-end lithium-ion, and that is not lithium iron phosphate, which lasts a lot longer, even though it costs more. So down in the long run, lithium iron phosphate is more cost effective energy wise, although it has pretty slightly better specs than the Tesla Powerwall. It's really more of a long-term cost effectiveness play. Remember, we saw earlier the lithium iron phosphate having a 80% depth of discharge, 10,000 cycle rating. Well, this is a battery technology that only has a 4,000 cycle rating, and yet I'm telling you it's higher end than lithium iron phosphate. Even though the cycle rating on this battery is more like the lifetime of the Tesla Powerwall. And this battery costs about the same as lithium iron phosphate. So it costs about the same amount of money per kilowatt hour, but it doesn't have nearly the cycle rating per kilowatt hour as lithium iron phosphate. So how would this be a more valuable battery than lithium iron phosphate? Let's see. We're gonna look at the spec sheets in a minute. Here's the spec sheet that I wanted. Since we're on the thought, we're just gonna pick it up and then we'll go back and look at the slides we skipped. But if we look at this, this is called lithium nickel metal batteries. So sometimes it's NCM. I've seen it as NMC. When I talked with Hawker, who is a top 3 lead acid forklift battery manufacturer, and I use them for my off-grid homes usually. The lithium-ion battery that they're coming to market with is a lithium NMC battery. And it makes sense. Hawker's main business is not to sell solar installers, off-grid residential batteries. Their main business is forklift batteries. So they have a large number of commercial customers, and they see this as the commercial battery technology. And here's why. We see their continuous discharge current or charge current is 114 amps. And for a very short time, less than 10 seconds, they can surge up to 285 amps. And less than 2 minutes, they can surge up to 228 amps. But a volt times an amp is a watt, and they're saying their battery has 222 watt hours to it. And so if it has 222 watt hours, and it's at 3.7 volt, or so it's 222 watt hours, and we can discharge it at 114 amps. Continuously. What we're essentially saying is that we can discharge this battery, at a very high rate of discharge. So let's see. I put the math in here. I want to think about it. So what we're saying is 200, 0.222 kilowatt hours, divided by 114 amps is something that I thought it was even. To me, this is. Yeah, so here we go. The C rate. Oh, this is even faster than I thought it would, because if it's holding 0.22 kilowatt hours and you discharge it at 114 amps. Here we go. So 114 amps times 3.7 volts is 421 kilowatt out. Is 421 watts. And this is 222 watt hours. So let's show you how I did that again. Let's assume we're not going into the rapid, even faster discharge rates. We're using the continuous output of 114 amps at 3.7 volts. So volt times an amp is a watt. So 114 amps times 3.7 volts is we're discharging this thing at a rate of 420 watts. And so if it stores 222 watt hours and we're discharging it at 3.7 volts divided by 114 amps, it's taking us a half an hour to fully discharge the battery. And so that means that this lithium NCM, as they call it, but it's sometimes called lithium NMC, the Delta battery, they're saying, well, you can fully discharge our battery in a half an hour, no problem. We'll give you a continuous rating for that. And so if I'm like that Colorado dentist office, and I only want to buy a small battery for leveling only half-hour loads, they're basically saying the lithium NCM is something that is for the spikiest of spikes. And so when you think about it, compared to a lithium iron phosphate that is still a continuous 2-hour battery, versus the lithium NMC, which they're giving you a rating for a continuous half-an-hour battery, you can get away with a smaller battery, substantially less capital expenditure required if your load is particularly spiky. So, if you have a load that is only on for an hour or less. Those heaters that turn on an hour before the people show up for work. The agricultural grain mill where they only feed the cows once a day, and so they have a giant spike right at 4 a.m., but it's done by 5 a.m. You may only have a surge load that lasts for a very short period of time, at which point the lithium NCM technology would be particularly valuable. I think I'm going the wrong way here. Yeah. So now we're back. So this is a Delta product. Put in some spec sheets. Each cabinet has a maximum discharge rate of 300 amps, so they probably have two these batteries are probably up to high voltage by the time you get to the top, and then they're wired in parallel. Let's see. They have air-conditioned shipping containers, for thermal management. A 20-foot container, some sizes, so you can start thinking, okay, well, if I have a super high load level, this is, you can fit about half a megawatt, or in a 20-foot container. In a 40-foot container, 1.5 megawatt hours. And then we also see, look, they're confirming that 2C discharge rate where they're saying, we're only putting 0.5 megawatt hour of storage in our container, but we're giving you a maximum power output of 1 megawatt. So whereas this is a 1 to 2 ratio, whereas what we saw the Tesla Powerwall was 5 kilowatts of output for a 13.5 kilowatt hour battery, which was less than 1 to 1.5. And so, whereas I look at lithium iron phosphate as being like a quality upgrade compared to the Tesla Powerwall, lithium NMC batteries are like a turbocharger or a hot rod where you're getting a lot more acceleration out of the battery instead of longevity for the same cost as the longevity battery. And so sometimes for particularly spiky loads, you need the acceleration rather than the longevity. So I talked with someone who actually installed these things, and so I asked them what like common configurations are, and what he's saying is they even go further than that, with 250 kilowatts of output, with what he's probably saying is 125 kilowatt output with 48 kilowatt hours of storage. Generally 1 or 2 per job site. And so he's saying that the batteries can actually surge up to 6C. So remember, we were looking at a 2C rate as the continuous output, whereas they're saying, you go look at the burst ratings and they go up to 6C, which is pretty true. Burst modes are usually 2 to 3 times what the continuous mode is. And a higher quality battery should have a higher burst rating as a raw metric. And so in their case, their solar array was AC coupled. And he says, one of these units that he says that the real market that he sees in applications is 50 to 100 kilowatts. So kind of just one unit, one cabinet, and one cabinet of batteries and one power conditioning system is kind of where he sees the demand management market. And so I asked him, I was like, well, why can't, when you have an incredibly spiky load, why can't you just manage your load control and not worry about batteries? Why can't you just do this with software controls or better facility planning? Why can't the dentist office turn the heater on at 4 a.m. instead of 6 a.m.? And so what he's saying is, in his case, in his application, I don't know what application it was, but I would guess it was like a food processing facility. And so they have certain motors and ovens that have to be used at a very particular time, and they just can't avoid not using those up high loads. I say food, it could be a manufacturing process. They may be using electric heaters to achieve a high temperature range, and they just can't do anything else about it otherwise, like a kiln. And so, an electric kiln is such a high load that your other loads don't matter. And if your business is to use an electric kiln, then you can't use load control. You have to have, a battery to go after it. And so he's looking at other applications that require a system, a staged power down or power up that is only required for a short period of time. So like, let's say a fiber optic network loses power from the grid and goes through a blackout, which would be a terrible thing to happen to this fiber optic network. But let's assume that it hit the iceberg and it's going down. It would be beneficial to have about 10 minutes of power at a very high demand output to catch the power down and do it in a staged manner, get everyone to the lifeboats. And so they don't need a 2-hour battery for that. They only need a 15-minute battery for that, or a half an hour battery for that. So, lithium NMC is a more rapid rate of discharge than lithium cobalt, which is the lower end lithium range that's cheaper. And so the lithium ion industry is still undergoing shifts in technology, where we don't quite, where even lithium cobalt and lithium titanate, they're saying could be swapped out down the road for latest and greatest technologies. Now that said, the market might drive that, where there may be a larger market for 2-hour batteries or 6-hour batteries. And so, we might see less demand for rapid discharge batteries as a whole. And so I don't think necessarily that low end lithium ion is going anywhere. I think it's going to keep growing. I think lithium iron phosphate will keep growing. I think lithium NMC will keep growing. Although what excites me most for commercial applications is lithium NMC. What goes into a battery cost? What we're seeing is just the electrodes. Not so much the electrolyte. It's the electrodes that degrade. Particularly it's the negative electrode that degrades the fastest. The electrodes are the tips that go into the liquid that the electrons, pass through the liquid in through the tip. And they're like teeth that bite into a juicy tomato, and the teeth develop plaque on them that eventually the electrons can't push through. And actually, a higher quality electrode, when it does finally degrade, the degradation is much harder to scrub. So there are more concerns about recycling higher end lithium ion batteries than there are about recycling lead acid. They're harder to dispose. So, labor and overhead doesn't have much room to shrink in the battery market. So we see lithium NMC batteries ranging in the $450 to $670 a kilowatt hour for the battery. That would not include the inverter. So earlier we were looking at installed pricing of Tesla Powerwalls being around $700 a kilowatt hour. Well, just the battery itself for lithium NMC is going to be $700 a kilowatt hour. So, it is a better app. It would only be cost effective for leveling, 30-minute to maybe 1 hour loads. If your peak load, if your demand management says you're going to keep going and do a larger system, and so instead of leveling a 30-minute load, you're now leveling a 2-hour load, at that point, it might be better to just consider lower end storage options. And so we see lithium iron phosphate costing about twice as much as low-end lithium ion. Lithium NMC, there's more lithium iron phosphate available than lithium NMC. So I guess I kind of misspoke. Lithium NMC is a more expensive technology. Um, I would say the lithium titanate pricing looks really good, but you're not going to find lithium titanate from any quality, reputable suppliers. So I got that pricing just off of random strangers spamming me on LinkedIn. So it's not really something I would take take it with a grain of salt. And then this is pricing estimates from the supercapacitor company, which again, there's the way I found out about this company is I participate in solar discussion boards in Australia. And in Australia, they get better access to Chinese supply chains. They have higher costs of electricity, and so they tend to use higher end products. And that's where the supercapacitor company is located. And so, it follows that there are solar installers who are evaluating this supercapacitor company and saying, we think you're just making a lithium titanate battery and calling it a supercapacitor unless you can show us a little bit more. They're still a fledgling company. So it's really manufacturing of scale that's going to be driving down the costs um, of lithium ion batteries. You know, Despite the cost decrease, so like Tesla is saying that they're buying their batteries now for under $200 a kilowatt hour. but by the time you go and buy the inverter and everything else, you're paying, $400 to $500 a kilowatt hour, and then the rest of the project costs, the labor, balance of system material, pushes that up to $700 a kilowatt hour. When you look at the product of the Tesla Powerwall at maybe the inverter plus the battery costing $500 a kilowatt hour, I haven't seen much of a price drop in the supply chain for lithium iron or lithium iron phosphate batteries over the last couple of years. So people keep talking about the price drop, anticipating the price drop, and what I would say is the price drop hasn't really happened yet, at least to the consumer building market. Now, it seems like Tesla has refocused its battery market to be more geared towards commercial application, and they have a product that's not called the Powerwall, but is instead called the Power Pack, and it is a little bit cheaper than the Powerwall. So, what I would say is I don't think the drop in lithium-ion battery pricing, first it's going to go to the electric vehicle market because that's where the purchasing volume is. And then second, it's going to go to utility scale and commercial applications because of purchasing volume. When I do off-grid, I really look at doing lead acid today and lithium ion 10 years from now, rather than thinking that lithium iron pricing is going to be so widespread. So anyway, if the price decrease really hasn't hit the market yet, that would be a reason to go with lower end lithium ion technology and run the battery into the ground and get your value out of it, and then see what you can replace it with 10 years down the road. This is a interesting chart. It really should be in my off-grid class. But what I did is I charted the cycle life versus depth of discharge for the Tesla Powerwall. And then I did it against, this is a forklift battery. N stands for industrial. So this is a forklift battery right here. This is the Tesla Powerwall. This is a forklift. And then these other two lines at the bottom are what are commonly marketed not as golf cart batteries or stuff that's more low end, but as renewable or premium flooded lead acid. And so the real takeaway from this graphic is I just wanted to show particularly in my off-grid class, I kind of espouse the value of unsealed flooded lead acid batteries. And it's just showing that the performance curve, it's not quite lithium ion. The cycles aren't quite what lithium ion will do. The responsiveness is not quite what lithium ion will do. But it's actually a lot closer to lithium ion in terms of performance than lower end lead acid. And if you went and you added lithium iron phosphate or lithium titanate, really what we would see is a spectrum of performance and price across multiple battery chemistries. Really to say that I wouldn't get too hung up on the difference between lead acid and lithium ion. It's more of a broader spectrum than what most kind of kitschy pop solar magazine articles portray it. We're talking about some system architecture. You really have two choices of DC versus AC coupling for combining your solar array and your battery. We use DC coupling a lot in off-grid because if the sun goes down and then the batteries lose power, the inverter turns off. And in a DC coupled system, the system has the ability for that when the sun comes back up to automatically recharge the batteries and then turn the power back on. So that's like a worst case scenario for an off-grid customer is they run out of power at 3 a.m. because they mismanaged their energy, but they don't really have to do anything other than wait for the sun to come back up to get power back on again. Under an AC coupling, if the grid goes out, your solar array turns off, but if there's no power in your battery bank, the solar array can't turn the battery inverter back on again. It can't turn on its own inverter. It has to see a grid signal to turn back on. And so in our off-grid class, we say DC coupling may be better than AC coupling. Technically, DC coupling should be more efficient than AC coupling too, but the reality is charge controllers, which are a DC to DC product, are relatively few and far between. And what that means is inverters, which are AC to DC product, they should be more expensive than charge controllers. But because inverters are so widespread, everyone has a batteryless solar inverter that just connects to the grid. It doesn't use batteries. It just dumps all the solar power directly into the load. There's so much money in the batteryless solar inverter market that these inverters are actually cheaper than the equivalent charge controllers in most cases. You really have to get into like specialty solar supply chain products to find DC charge controllers, but they do exist. There's one called Amped, which I really admire them. They do a 1,000-volt charge controller, and so they take all the fluctuating voltage coming out of the solar array, and they can run it into a 1,000-volt battery bank. It's pretty cool. It's very efficient, and it's not too expensive. I wouldn't get too hung up on AC versus DC coupling. On a commercial facility, it's usually going to be easier to have your battery in one location and your solar array in another location. And so when they're in different areas of the facility, AC coupling is the way to go. You're not really trying to do this for power backup or critical loads like you would in an off-grid setting. And furthermore, if the batteries run out and the grid goes down and your solar array turns off, another way to turn it back on again is to have a spare battery or to program a little bit of reserve capacity so that it doesn't run out, or just to use a generator. So, in most cases, I'd say you're going to have an AC coupled system where the solar array is on its own inverter, and the battery is on its own inverter. And that also means you can retrofit existing solar arrays pretty easily to be a solar peaker as well. The important part is you have to show that you're only charging the battery when the solar array is on so that you can claim the tax credit. You can't charge the batteries at night if you're saying that the batteries are charged by solar power. You have to constrain the charge time if you want to claim that tax credit. Again, that might be a reason for intelligent controls because you might benefit from saying, okay, well, let's return 1% of the tax credit because we want to do a little bit more demand management because where our load is much higher because we're having a record heat wave. You know, there might be an easy answer for that, but the sky's the limit on what intelligent algorithms could be applied to demand management. While we're on the topic, I think I was trying to pull this up before class when the power went out. This is kind of an interesting one where they use similar concepts for utility scale participation. Here's a apartment complex in Utah where they say it's going to be used as a virtual power plant where every single unit in the apartment complex has a lithium-ion battery. Here's a residential solar company that partnered with the local power company in order to provide incentives for batteries that in exchange give the power company access to the batteries at a certain time. Grids, electric grids may have demand pricing too. You either have a regulated grid where there's no competition and the power grid operator is going to have to eat the costs of heavy demand. And so on a regulated grid, you might have higher demand charges than on a deregulated grid. In Texas, you have a deregulated market, which means you get all kinds of electric rate structures. If you're a large enough facility, you might have a real-time electricity pricing rate structure in Texas, which is almost the same as being a power provider where your rate is based on the Dow Jones Industrial Average of electricity pricing in Texas. Texas has an auction market at the big energy level where it's a combination of long-term contracts and short-term contracts and even shorter-term energy options and penalties if your customers use more energy than what you had contracted for. You might get stuck with the person that buys this divide by 1,000 $9 per kilowatt hour electricity pricing in Texas at the utility scale market during certain times when the grid hits its peak load capacity and it doesn't have the supply for it. Let's see, does this article have any nice fancy graphs for us? I don't see any. But anyway, what's interesting about the hotel that can be a power plant or the Green Mountain Energy that turns residential lithium-ion batteries into a power plant is to take advantage of demand level pricing at the utility scale. And those would be examples of AC coupled systems, which could be spread throughout a facility, protecting critical loads at the service panel, but still, injecting juice from the battery during peak demand times. So AC coupling is a valid option for solar peakers. DC coupling would be the more rare option that you would probably only get if you're doing a major energy overhaul and you're getting those, Delta shipping containers that sit alongside the building. I think in other words, there's not many solutions on the market that will do a DC direct link between the solar array and the battery. These are kind of residential slides, so I'm kind of get through them. Now this is kind of what a DC coupled system would look like. Is you have your solar array and then a charge controller that gets the solar array to the same voltage as the battery. And the advantage is that way you only need to have one inverter. But the disadvantage, there's a couple disadvantages to that. The first is you still have to buy the charge controller, and that can be almost as costly as the inverter. The second is that if you have the solar array also on their own inverters, then you can, not use the battery inverter when the solar array is doing its job. So while you might not have followed that all the way through, the takeaway is AC coupling is probably the better architecture for commercial solar peakers. By the way, because we haven't mentioned this yet, I have a YouTube channel, and I don't really go out of my way to publicize it. But the reason why I mention it, you can always email me for this, but I put the course recordings onto the YouTube channel so that you can go back to it. I'm going to skip over this wiring diagrams. Let's just do it real quick. This is just a schematic of a solar array that is. This one's actually DC coupled. The solar arrays are on their own charge controllers. The circuits are being brought back to on this electric service. There's actually a DC side to the panel and an AC side to the panel. Charge controllers are connected to the battery. The inverters are connected to the battery, and the inverters are also connected to the AC side of the facility load breakers in combination with the electric grid. This stuff right here is just a way of transferring the power to a critical load panel that would still have power when the grid goes down. But what's this particular inverter is a bidirectional inverter, so it's also capable of backfeeding the grid. And what's interesting about these inverters, this is a Schneider product, and it's a stackable inverter, so you can put as many of these inverters next to each other as you want, and they're about 7 kilowatts each. So you could build a small solar peaker out of, these kind of residential battery inverters, all the way up to 50 kilowatts. Let's say Tesla is not giving you the ability to order their products because they're selling so many of them, they don't want to go to you. They have a backlog, they got orders to fill already, they can't accept any more orders. You might say, okay, well, I'm going to go buy another battery inverter and someone else's lithium-ion battery and just make my own. You could come out looking like this, where you're stacking a bunch of battery inverters next to each other. And then these inverters have the option of being programmed in either like residential off-grid setting, or they have a internet connection, and that gets traced all the way back to the grid where you have another meter. And instead of programming the battery inverters to always be on, you just program them to squirt their battery juice into the grid whenever the load from the grid rises above a predetermined threshold. So anyway, I recommend AC coupling for commercial solar peakers because not only do you get the inverter capacity of the battery inverter, but then during the day, you get the inverter capacity of your solar array so that your battery inverter doesn't need to work as hard, and so it'll last longer. These are effectively examples of where the charge controllers would go up on the rooftop. Generally, they're going to do more than just, there's more advantage to them than just regulating the voltage back to a battery bank. Often, they'll serve to step up the voltage. And when you increase voltage, you decrease amperage. You can get more power through the same cable. So, the DC coupling of commercial solar batteries will not vanish completely, but it's not a necessity as some think it is in residential off grid. Okay, so since this is a commercial solar class, I wanted to talk about a couple of issues that I feel are pretty important. One, I just got done doing a commercial solar project in West Virginia, and the main problem with the project is it was on a flat commercial roof. And don't get me wrong, there's nothing better than doing a project on a flat commercial roof compared to a residential rooftop. Having the roof be flat is fine with me. The problem with flat commercial roofs is that they become, lakes whenever it rains. There's especially large flat rooftops. In our case, this is not photos from the same project, but in our case, on this recent project, wherever there was a drain for water, there was an embankment around the drain that lifted the roof up by 2 or 3 inches, and so the water could not make it to the drain. And generally, the edge of the roof is going to be a little bit taller than the middle, and so the water would just sit on top of the roof. It wouldn't drain, it wouldn't go to the edge. And now we're talking about putting high voltage solar right on top of standing pools of water. And the problem is a lot of commercial solar system racking systems are cheap. Not all, but most. And they use these ballast pans to weight the solar down with concrete, but then the solar array really just sits right on top of the roof. And so there's only a couple inches of space between the solar array and the roof. And the solar array is going to have wires that kind of connect to the next door neighbor. And so some of you may have been reading about the fires that Walmart is accusing Tesla of, and it's not uncommon for these cables to droop down on that roof deck. And if one of the connectors between the 2 solar arrays droops down onto the roof deck where there's a puddle of water, it's going to cause a ground fault. That water will take the current into the rack, and it'll, if it all goes well, the inverter will detect a ground fault and it won't, turn on. That's not always the case. And if anything, even if the inverter turns off, it's still not going to stop the ground fault from occurring. You need to get a guy out there and fix it, pretty quickly. So I have a preference for racking systems that kind of elevate the solar array off the roof deck. And one thing that's interesting is they don't require this concrete. And in fact, what we're doing here is supporting the array on pipe blocks. and only the anchors of the solar array are the endpoints of the solar array are anchored into the roof. And so the other source of fire on commercial solar is when you have these cables. Let me get a good these cables that are connecting to the solar panels. Generally, you do cable management to get it up here. Of course, this is a nice long rail, and this rail has a little I-beam in it so that we can put the cable up here. On this kind of cheap system, there's no rail for the solar cables to get secured to. And so it's a much more difficult job to do cable management on the very cheapest of commercial solar rackings, and especially if you use the type of racking that sits right on the roof, and especially if there's a drainage issue on your roof where water consistently ponds on the roof rather than getting to the drain. You're just asking for a long-term safety issue with your commercial solar racking. So I would strongly suggest to use a commercial solar rack that has consideration for cable management, because again, these modules are going to be plugging into their next door neighbor. Even better is an elevated racking system because your cables are that much further off the top of the roof deck. So anyway, the moral of the story is I would strongly suggest going with a higher end racking system rather than a lower end racking system. It is not that difficult to patch and seal a hole in a commercial roof. Every air conditioner unit on a rooftop has a giant hole associated in the rooftop with it. You just have to have a roofing contractor be involved in your project. Okay, look, we're almost done with this section, so let me move on, and we'll take a break. This is really an off-grid slide, so I'm not going to cover it too much. Other than to say this is a configuration where the whole building runs off-grid, and then the battery gets charged from the grid. But the solar array and even sometimes the output capacity of the battery are fully isolated from the grid. But if the system should fail, instead of having a backup generator, you can use the grid for backup. Now that's kind of interesting in the sense where if you do your solar peaker and you start wrecking the utility revenue, and enough people do it, it's still gonna. This is 10 years from now, but just like utilities are looking at increasing the fixed costs of grid connections on their residential customers, the fact that you're making your energy facility more efficient is going to upset them, and they're going to say, well, maybe we should have some discriminatory rate structures for commercial businesses who are managing their electricity and generating their own electricity. And in this grid assist configuration, you can actually take the whole building offline, although provided, as we talked about earlier, whole building power is a much more intense project. So I don't know. We do this in Mississippi for off-grid. What it allows us to do is not do a full-blown off-grid system. We can give them the inverter capacity they need, but we don't need to do so large a solar array or so large a battery, but just something that's kind of better budget friendly. This slide is really just a residential issue. You're always going to have high voltage circuits at the commercial level. You might even go up to 1,000 volt circuits at the commercial level. So you have longer circuits than you do at the residential level. There's some battery products at the residential level that are only low voltage, and it can surprise you when you start getting much shorter circuits if you use lower voltage product. Okay, so we've kind of concluded that if you have high demand charges, that a solar peaker plant is the most cost-effective kind of application of solar out there. And remember, it's because, fundamentally solar provides peak demand electricity, but without storage, it cannot deliver, 30 days in a row. It can't go out and pitch a no-hitter where every single time you're getting peak demand reduction from the facility, and there's more to it than that. There's the morning peak and the evening peak to deal with. So even though solar produces peak demand energy, the facility is being charged by peak demand power. And that difference is enough for there to be very little savings with solar by itself. But then when you add batteries on top of it, it's like the exact opposite. It's the greatest savings out there. Much better than residential energy rates. The solar industry was wrong to fight with Arizona Power about pushing solar customers onto demand charges. What they should have said is keep going, give the solar customers the highest demand charges possible, because a solar array really is incomplete without a battery. And demand charges are battery friendly, and the grid needs batteries. That's its main problem, is lack of storage. It's never had storage. So now we have an opportunity for the most cost-effective solar project possible that is grid-tied, that does not need net metering. But it's still very expensive, of course. You can get loans to finance these projects. If you have qualified clients who are willing to go out and get a loan, the financing company can take care of everything else. Same with installation contractors and construction financing. These projects are large, and that can attract a kind of financial specialists who are financing much less lucrative projects. So anyway, I want to take a step sideways and talk about community purchasing of green energy and how it's kind of been right to be skeptical when the power company is offering you a green energy plan. Before solar was so popular, wind energy and voluntary wind energy was in fashion. The utility would say, we can sign you up to 100% green power plan. And it's in one way it's ridiculous because you're getting the exact same electricity as you otherwise would be. They're not directing all the green electrons directly into your circuit. It all gets mixed together. But they're committing to take your money and put it to use in support of green energy. And if you read the fine print, they'll also say education. So they can redirect it into overhead. And so you might just be paying for the power company's overhead by signing up for a green energy plan. And the proof of that is if you look at the average price, the average premium of what the utility would charge for green energy, What this graph is showing is up to $20 a megawatt hour. So if we have $20 a megawatt hour, you divide by 1,000 to get kilowatt hours, and you get 2 cents a kilowatt hour. And so like that green energy plan would cost the customer anywhere from half a cent a kilowatt hour up to, generally around a penny or a penny and a half a kilowatt hour. It's a premium that the utility charges you to sell you a 100% green energy plan. And that was how, the utility would get money to put towards green energy stuff, presumably. The average cost of the what they were doing. So there's for lack of a better term, let's call it cap and trade. So there's a system where wind projects, green energy generators would log their production, and in return they would get the right to sell they call them something different, but let's say carbon credit that the system produces. They're called renewable energy credits or RECs. It's a renewable energy credit. And the cost of the renewable energy credit is 1/10 of a penny a kilowatt hour, and they were selling them to customers for up to 2 pennies a kilowatt hour. So they were buying them for 1/10 of a penny, and they're selling them for up to 2 pennies. And in some cases, it got even worse. I've seen it up for 12 pennies, although they didn't get any subscribers and canceled the program. I've seen it for 4.5 pennies. Now, a lot of power companies will sell it to you for $10 a month, and they'll sell it to you for 5 pennies. They'll mark it up real big. But the average cost of these renewable energy credits is 1/10 of a penny. And so fundamentally, the vast majority of these utility voluntary green energy programs resulted in the customer's money, 95% of it going into overhead and only 5% of it going into actual green project compensation. So you could argue that those who opened up their wallets and voluntarily gave cash for green projects, you could argue that more of their money just went into making the bottom line more profitable for the fossil fuel-based company. So if you want to ridicule voluntary green energy programs, I'd say go right ahead. There's data to back that up. On the other hand, when you talk to customers about why they voluntarily purchase green energy, they'll say, well, I can't put a $20,000 solar array on my home. I'm just glad the utility gives me the option to pay them a little bit of money to do green things, better than it makes me feel like I'm doing something. And they get that value from it. And the utility does do some green things. So, maybe it's a little bit of direct monetary activism to get the utility's attention. What I think is interesting about that is there's a lot of do-gooders out there in the community who are willing to pay, not just save money by doing solar power, but pay a little bit of a premium to, in a lesser way, participate in helping the grid be green. And that's where the value of community solar really comes in, because the short of it is community solar is where multiple members of the community can buy into a project and see it come out of the ground. So instead of this very murky, where is my renewable energy credit coming from? Because the power company wouldn't tell you. They weren't traceable down to the consumer. You just have to take the power company's word for it. There's no, there is now a blockchain for solar energy that you can record this stuff on called SolarCoin. But calling up a utility and asking them where their renewable energy credit came from, there's no verification process on that, and some companies have gotten in trouble for not documenting these credits that they're selling their customers. So community solar is coming in and replacing voluntary green energy plans because you can't fake it. It's there, you can see it. Maybe you're paying a premium, maybe you're getting your money back over a long-term time, but you're seeing the project come out of the ground. And there's no reason why the utility has to control this process. You can do it yourself with your own commercial solar peaker plant. So here's an example of a project, and most community solar projects today are developed through direct power purchase agreement with the utility. But the value of those PPAs is going down and down and down and down to the point where you have to do 100-megawatt solar farms in order to make the projects happen. And so that leaves out this whole swath of commercial-sized projects that actually have really good paybacks. So so when we're looking at these community solar programs, the economics of doing the same thing on a commercial solar peaker should be able to exceed what these programs are resulting in. I actually called Geronimo and asked them for details on their community solar program, and they kindly told me that they would not answer any of my questions, to the point where one of their VPs emailed me to say he wouldn't answer the questions out of respect for customer privacy. And since I wasn't up in Minnesota to sign up for their program, out of respect for customer privacy, they wouldn't tell me anything about it. So I went and I found some customers and asked them, and I say this because this is one of the more popular community solar programs in the country. I'd say they're market leaders, and that's Minnesota. They decided that their solar thing would be community solar, and so they've done a lot of experimentation with it. And so what this customer is basically saying is he participates in it, and what it is he gets a flat rate for 25 years. And he says it's a bit of a gamble. I may save money over 25 years, or I may end up paying a little extra to offset my usage. So basically what the Minnesota program does is it gives you a 25-year contract by increasing your price of electricity by 2 cents a kilowatt hour. So it's like, you think about it, you go to a utility and you're like, hey, I can get this customer to agree to increase their price of electricity by 15% today for 25 years under contract. Do you want to take that deal or not? Utilities, especially right now with, declining revenue because of, whatever reason, they say declining revenue because of solar, whatever. They're facing declining revenue, higher costs. You come to them with an opportunity to lock in their customers so they don't have to worry about deregulation and increase the price of electricity. Usually they have to lobby to get the price of electricity to increase. Now they're having customers line up outside their door to increase the price of their own electricity. That's who community solar project customers are. They're willing to pay a little bit more to see a project come out of the ground on a promise that not even a promise, just on maybe they'll save some money over time. But we're talking about 20 or 25-year repayments, which a CFO would not normally approve of. These are do-gooders who are willing to pay a little bit more for their electricity so that they can see the project come out of the ground. But I say, well, how important is a flat rate for 25 years to you? And he's like, that's not really why I'm doing it. I'm doing it to support, local renewables. In Massachusetts, they have a community solar program, and what's interesting about their program as opposed to Minnesota is you actually immediately start saving money. So you pick up your phone in Massachusetts, you're like signing up for community solar, immediately your electric rate goes down 5 to 10%. Like, well, how does that make sense? That doesn't make any sense at all. Well, and sorry, this is Massachusetts as compared to Minnesota. Well, Massachusetts has a market for those renewable energy credits, those carbon credits for solar that we talked about, and they're valuing them nowadays at about $300 per megawatt hour, or in other words, 30 cents per kilowatt hour. And the price of electricity in Massachusetts is expensive. It's like 18 or 19, let's just call it 20 cents a kilowatt hour. But the value of the solar carbon credit is 30 cents a kilowatt hour. So it's more than double the price of electricity. And so what a company like this Massachusetts community solar program is doing is they're getting permission to build these utility scale solar projects because they are community solar projects. And so they go and get customers signed up, and they say, okay, I have 1,000 customers willing to buy the electricity from this power plant over the course of 25 years. And so give me permission to build the power plant, and it's solar. And so they go and they build the power plant, and because they're getting not just the 90% of the retail price of electricity from the customer, but they're also getting 150% of the retail price of electricity because of the solar credit. And so they're actually making money hand over fist, and that's why they're able to cut the participant in on the deal by giving them a discount of 5 to 10% off of their electric bill. And so, because of the subsidy in Massachusetts for solar, a community solar model where the customer gets an immediate discount on their electric bill comes into play. And so in the Minnesota model, the customer, there's not really subsidies, but the customers are agreeing to increase the price of their electricity by a little bit over a 25-year contract. And in the Massachusetts model, because there is such a big subsidy, the customers are saying, I'll sign up for 25 years at this fixed rate, and it might be 5 to 10% less than the current rate, but who knows, that might be a good hedge for the power company to make too, to lock you in at something less, but for that 25-year contract. Anyway, the more energy resources that come to the grid, the cheaper electricity should get. So maybe the price of electricity will just go down. Maybe we'll have free electricity and it'll all be demand charges. That could be one way to do it. And so in Massachusetts and in Minnesota, the customer is agreeing for 25 years to be a community solar participant, and they get a slight adjustment to their electric bill. In Minnesota, the customers self-fund the program by increasing their price of electricity. And in Massachusetts, the customers are drawn into the program because there's giant subsidy checks available, and they're cutting they're keeping most of the subsidy for themselves, for better or worse, but they're cutting the customer in on a little bit of the subsidy and signing them up to buy electricity for 25 years. And then Michigan comes along and says, okay, well, in the last two cases, customers are agreeing to fund the loan payments of the project. They're paying as they go over a long period of time, but that still doesn't come up with the capital to finance the project at the get-go. Or maybe, as soon as it's built, having the money taken from the customer at that time. So I can cover the construction financing. I need the customer base to be ready to buy the project as soon as it comes out of the ground. And so what Michigan does is you get a couple of different options. You can either pay a lump sum up front for your unit or block of community solar, or you can finance that block over 25 years. And so if you pay the upfront lump sum, you put in an investment and you might get your money back after 15 years. Whereas if you do the $10 a month, you're probably going to end up just paying an extra $10 a month on your electric bill in support of the local solar project. It's probably never going to pay back. But at any rate, what's interesting about the Michigan program is you take the price of the 500-watt block for $1,289. So they're buying a 500-watt solar panel. And it's installed at $360 a watt. That's actually a really good price. You cannot pay me $360 a watt to go and put 500 watts of solar on your rooftop. That's too small a project for me to be interested in. So it's not such a good price when you're buying 10 kilowatts worth, because you might be able to get that installed at $250 a watt. On the other hand, you don't have to ever worry about it. You're going to get your money, and it's going to be just credited off your electric bill directly. And so, and you don't know what you're buying. Well, the thing is, at $360 a watt, they're going to get a 25-year payback on their project. So they're not, they're going to get their money back, but they're spending money and getting it back, and then just maybe breaking even. So what they're really doing by doing this is putting up $1,300 to participate in community solar and getting their money back maybe by the end of the program. Now, I'll tell you what, I've seen worse in the solar industry. That's not something that I try to do with my own pricing and practice. I'm more interested in selling cost-effective systems. But I've seen customers with other sales reps get talked into much more expensive solar arrays at much greater risk. And there's people out there who want to participate in these programs because they have the money to spend now, and they want to make sure their electric bill is taken care of for the next 25 years. Like retirees who know they're not moving anywhere, they may want to get their spouse set up for long term. And so if they can give their money to the power company to build a power solar plant and not have an electric bill, they might not be so worried about the economics as long as they know they're going to get what's being delivered. And then if you look at the $10 a month subscription, that comes out to be 19 cents a kilowatt hour. So if you go with a $10 a month plan, you're actually increasing your electricity by 28%, but only for the portion that you buy into. So, again, you're really just slightly increasing you're taking $7 worth of electricity, and now it's going to cost you $10. So it's not a huge participation fee to feel like you're involved. If I were planning my own community solar project, I probably would not have such a small transaction fee. The overhead and administrative costs would be pretty large. Or you do something like that so that you can have a lot of people participating, and you take advantage of the publicity that way. But regardless, the thing that's interesting is that the participant is willing to pay a little bit more each month on their electric bill in support of local green energy. Uh, Solar leasing used to be on the rise. Third-party solar used to be on the rise. Now it's moving back towards a customer-owned market. I would say that the rise of third-party owned solar was launched on the back of heavy solar subsidies, and businesses were formed to kind of go after these subsidies. And now that the big subsidy wave is over at the state and local level, we're moving back towards customer-owned arrays. What that might mean is you might it might take a new business model to get third-party owned solar back on the market. If you wanted to write your own community solar program, what does that mean? When you're a community solar subscriber, and let's say you were a third-party participant. So, like one example is Solar City or Sunrun. Let's talk about Sunrun because they're actually still in business and aren't burning buildings down. Sunrun, they're partnering with power companies on batteries and doing innovative things. When you sign up for a solar lease from Sunrun, and what that means is they come and put solar on your rooftop, and you get whatever electric savings there are, and you pay them, $200 a month as your lease payment. And so hopefully you save more than $200 a month on a $200 a month lease payment. Otherwise, well, we hope you break even. But there are rules that apply to that sort of agreement. And they're not just specific rules for solar, they're specific rules for, general leasing, principles. And a lot of it has to do with depreciation and taxes and who gets to claim the depreciation. Residentially, you don't have depreciation, but you also don't pay tax on the money that the solar array generates. Commercial business, they claim depreciation, but they also pay tax on the money that the solar array generates because the solar array gives them money and now they're a profitable business and they owe tax on that profit. And so you don't want to crossover between residential and commercial because one is like a post-tax revenue stream without depreciation. The other is a taxable revenue stream with depreciation. You don't want the residential customer who's ineligible for depreciation but paying you money that you have to be taxed on to claim the depreciation. You want to claim it yourself. The residential customer is ineligible. That's generally how it goes, and then the red tape comes in and gives you additional caveats and exceptions. But an operating lease is generally how a third-party solar lease goes. And what an operating lease does is it keeps the lease provider on the hook for everything, and the lease participant is brought in just to use the equipment but not take long-term ownership of it. So an operating lease, the owner of the system is the lease provider. At the end of the lease provider comes and picks the system up, or the user can buy the asset for fair market value, whatever that is. It might be zero. The operating lease company may have fully depreciated the asset, and so on the books, the asset is worth nothing, and lo and behold, at the end of its life, someone will haul it off for scrap, but, you're not going to make any money out of the deal, and its fair market value is zero, or its fair market value is something greater than that, but you don't prearrange a fair market value buyout. If you think about a lease where you buy the lease out for $1 at the end of the lease term and you take ownership of whatever it is, that is a capital lease. That is not an operating lease. Operating leases, in order for the system owner to keep hold of the claim of ownership and therefore the claim of the tax credit, therefore the claim of depreciation, an operating lease is subject to certain rules. And those rules are the lease cannot be longer than 80% of the asset life. And that's why companies like Tesla are trying to argue for a longer asset life so that they can extend the length of their solar leases. The lease provider is responsible for insurance and maintenance of the array. Well, that doesn't sound too good for those Walmart fires, but I'm sure that's what Tesla is now realizing. And that's good because you're going to want to do these things. If you're the developer of the commercial solar peaker, you want to make sure that you're insuring and maintaining it. You want to be responsible for that. And guess what? Operating leases, the payment structure is usually it's going to be beneficial to the lease provider. Otherwise, they're not going to do it. So you're taking care of the insurance and maintenance, but you're making money off of the agreement. You're making profit off of those payments. There's different ways to do it. There used to be more of a debate on whether or not by offering community solar or solar leases, that you were a vendor of electricity. And where the guidance has pretty much come down on is as long as the participants' involvement is no greater than what they're spending in their electric bill, then they're really doing this to offset their electric bill rather than be an investor in an annuity. And so basically, when it comes down to that, the programs that are being allowed through with very little hubbub have the participants not participate for any more than 120% of their electric bill. You also sometimes see that in solar interconnection agreements, where it's like you're not allowed to interconnect a solar array no greater than 120% of your size. So I don't know if that's a coincidence or not. I don't think it is. But if you are concerned about directly tying the agreement to the price of electricity, where the customer is compensated so much per kilowatt hour or pays you so much per kilowatt hour, the other way to do it is to have a fixed monthly fee. But that's not to say you can't do it directly tied to the price of electricity. That's called, they call that a special lease agreement. It's called a services agreement. It's a form of an operating lease. And so there's very different ways to do an operating lease as opposed to a capital lease, which is generally a shorter term, but it can be a longer term. And at the end of the capital lease, effectively the person who's making the payments on the capital lease takes ownership of the asset. Likewise, the person making payments on a capital lease also takes depreciation and the tax credit. So a capital lease is more like a loan. An operating lease is more like a subscriber to your energy plan, where they're not going to own the power plant at the end of the thing. They're just paying you money for use of services. And so the way community solar effectively works is you get a bunch of subscribers willing to pay, either a series of payments, which gets, used for financing. A developer comes and says, I'll give you this much if I can take that. Or the members directly fund, the upfront cost by paying for it upfront. And instead of those owners, paying a series of money, instead of them paying the series money to someone else, instead if they pay up front, that series of money comes back to them. So community solar can actually work two ways. Someone could give you the money up front and you pay them, or someone can say, I'll commit for 25 years to pay you this, and then you come up with the money up front to do the project, and they pay you. One way or another, someone's going to come up with the money for the project, and someone's going to make a series of payments for the project. And the utility is in a good position to do community solar because all these customers already have accounts. And furthermore, the customer is on the hook. If they don't pay their electric bill, you turn the power off. There's a chance that the community solar participant could welch on their deal, and you won't be able to so directly cut their power off. At the same time, generally that's resolved by having these agreements be only cancelable under certain conditions, like they're moving away so that you can no longer credit their bill. I'm not sure if this company here's a company called Arcadia Power, and they do a community solar where basically you sign up and they connect you with a project, and then they take over your electric bill. So you pay them, and they pay your electric bill. So that's what they like about that is. What the customer likes about that is it gives them the perception of being solar powered, and what they like about that is, I guess, that gives them a little bit of ability to control your electric bill. Although I'm sure the customer could get out of that pretty quickly if they wanted to. But the reason why there's no risk for Arcadia Power is they opt for the model where the customer comes up with the money up front to fund the project, and then Arcadia Power credits their bill and makes the series of payments over a period of time. And hold on one sec. I used the wrong browser window for my presentation on this one, so let me. There we go. Let's go from there. And so there are private companies doing this, putting together community solar platforms that aren't associated with the utility, but they kind of toe a thin line between pretending to be a utility and being a community solar developer. So there's actually a blockchain out there called SolarCoin, where solar production gets logged publicly to a record. It's really a database of record keeping, like any other database of record keeping. In fact, back in the renewable energy credit era, and still today in states like Massachusetts, where they have renewable energy credit markets, there are databases of renewable energy production logs, because to generate a renewable energy credit, you had to log your production. You had to tell them how much you made so you could go legally claim to have such a credit. In a similar way, SolarCoin is a public log of solar production that is indelible. So if there's ever a lawsuit, people don't think that their production is being tracked, this is actually traceable. So unlike a renewable energy credit, which you cannot trace back to the wind farm, a blockchain can be used to, log solar production against public accounts that can be anonymous. And the reason why you do this is it's not that the customer is going to be guaranteed any more money than what the company who's supposed to pay them pays them, but this is a receipt. This is a document that says, the solar plant, generated so much energy, and that energy is allocated to these accounts, and these accounts are owed this much. And isn't that really what the role of a utility company is to hold these accounts so that you trust them with your production and they tell you what the bill is, and you trust that the meter is accurate. And a public ledger is even more trustworthy because you can compare the production against other solar owners and be, compare it against other solar arrays, like as if you could compare your electric bill to your neighbor's, which you can't currently do. So, I don't know if you don't, the problem with community solar, the problem with a company like Arcadia Solar is they don't have the same trustworthiness as the utility. So the utility doesn't really have to provide a receipt. Even though we may, have this, we have to pay your electric bill if you want electricity relationship with our power provider. You still trust them to do what they're going to do. You might not like your power company, but you trust your power company. A third-party community solar platform is less trustworthy than that. And so maybe having the record keeping be logged on a public blockchain is something to consider. But fundamentally, you can create a community solar program by writing a series of operating leases and having each participant sign an operating lease. And that operating lease could be, you give me $5,000 to own a block of the community solar array, and I will pay you so much money a month because you own that operating lease. And so, the risk is on the community participant, that you're going to pay them that money, but that's probably better than the other way around, where the risk is they're going to pay you. Who knows what's going to happen to them? And then this series of payments, because it's a third-party platform instead of tied to a utility, is in a way more valuable, because then it doesn't matter where the community solar participant lives, they're still entitled to that revenue stream, which again has not been considered a taxable revenue stream to them, so long as it is less than what they're paying on their electric bill. The guidance has been, as long as community solar is equal to or less than the electric bill, we are not considering this to be an investment. We are considering it to be a way for the customer to offset their electric bill because they do not otherwise want to have solar on their rooftop. And there's a lot of customers out there that applies to. And so, in other words, just by writing, having your community solar, program based on operating lease contracts is a nice starting point. And it might not be that your community solar participants are, the individual residents of a community. They could be corporate sponsors, who are buying, into the publicity of the project, as well as financing the project and getting a credit on their electric bill. And so this is pretty interesting, because on many customers who have especially higher demand charges, the higher the demand charge goes, the quicker the payback on these commercial solar peakers can get. These are paybacks that are under 8 years, whereas community solar participants are happy with paybacks that are closer to year 20 or beyond. And so what happens if, you build a project that is supposed to have an 8-year payback, and then you sell it to someone who is satisfied with a 20-year payback? The implication is the project just got more profitable because you can cash out the short-term investor at a markup and sell it to the long-term investor. And so that's really the purpose of community solar, is that there's a healthy number of altruists who would be happy to give you money for a solar project as long as they can participate in it. They don't have to be making money like an investment in the stock market. All they really have to do is have you pay their electric bill for the next 25 years and tell them how much money that's going to cost them. And even though they might not be making a prudent investment decision, it's not regulated like an investment. There's no expectation of a giant return on investment. The lawyers go out of their way to never mention how much money you're going to make on the project because they're not portraying it as an investment. It's really a way for the participant to fund a local solar project and get their electric bill offset in exchange for it over a long period of time. So long as you can make money off of it and still find participants, great. Now the reality is most customers do not want a 20-year payback on their solar projects. Most customers want, an 8-year or less payback on their solar project. If we want solar to be, 10% of the electric grid, the payback needs to be, 8 years. If we want solar to be, where half the, 40% of the people who hear about solar power go out and buy it, the payback has to be at year 3. So the transition to a 100% green electric bill, comes with a payback that is well under, 10 years, which is why I'm so harsh on expensive solar projects. But the community solar customer is way out here saying, I'm happy this way. And maybe they're not putting up $50,000 for a solar project. Maybe they're just putting up $5,000 for a share in the project. But there are, financial companies that will invest at this point. And so just the short of it is, if you have an opportunity for a solar peaker, that doesn't mean that you or the project financer has to be a long-term holder of that project. What you can do instead is, at least for the money side, if you develop the project under an 8-year payback, and then immediately at year 1, you launch your community solar program, and you start getting your money back from customers who are happy with a 20-year payback, you might be able to, you're putting more profit into the project, and you may be able to get out of your loan payment early. And so in other words, community solar provides a pathway to cash out a short-term investor ahead of his term. And why would they do that? Well, because they're getting all their profit and the project's actually even becoming more profitable, because whereas the short-term investor required an 8-year payback in order to fund the project, the community solar investor who's handing you money to cash them out with is happy with a 20-year payback. And so, that's your route to getting rid of the long-term risk, or offloading at least the financing of the long-term risk to the community. And what's interesting about that is there's plenty of residential markets where the solar policies for residential customers are so bad that the payback for solar in those areas is 20 years with maintenance plus insurance. In markets where, in Mississippi, I can get a 15-year payback or a 14-year payback on an off-grid array, but it's going to cost, over $50,000 to convert a basic home into a 100% off-grid home. And many solar customers, or at least people who want to be solar customers, don't have that kind of money to put up, but they might have $10,000. And so, the short of it is, if you're doing a commercial solar peaker and the economics show that you have an 8-year payback, you might want to consider also making it a community solar project as a way to, make even more money, get even more value off the project. And, you might not make much profit by developing the project and having it installed. Your profit might come as the community solar project gets fully subscribed. You might break even off of the development of the project, and your money comes from the success of the program. Or vice versa. You might offload it to someone who wants to manage the community solar platform in exchange for doing the array maintenance and insurance and administering the program. So how do you develop the model so that a CFO will smile? How do you, when it's time to go and make your presentation and say, I want to do a solar peaker, here are the economics. I've shown you a bit of a process for creating a model in a spreadsheet, taking your solar production, guessing the starting size of your battery bank, hard coding demand thresholds, starting out with the interval data, subtracting the solar, adding the batteries, seeing what you come out with. Now that's not going to be good enough to go in and present your $1 million project or more. Now, there's a software out there called Energy Toolbase that has really, what caught my attention is back, when I was in college, when we would do engineering economics exercises, we would make spreadsheets that look like this, that govern things like depreciation. Here we have the accelerated depreciation schedule. And what's also commonly missed by residential installers in particular, or people who are presenting economic models who really shouldn't be, is that if you get a depreciation and you're depreciating your asset, that's a tax incentive. But after the depreciation is fully claimed, if you're making $20,000 or $30,000 in solar leasing payments, you're going to pay taxes on those solar leasing payments. So, what Energy Toolbase does is a true, after-tax analysis. And they have your utility rate databases plugged in. They have the economics and depreciation and incentives plugged in for your individual state. And they calculate, internal rate of return, net present value, using discount factors and, the having the price of electricity increase or not increase. 2% is a pretty reasonable assumption. And, all the way down to your state taxes. They're an economic modeling tool, which, I don't know, I think they save a lot of time. Going back to it, just make sure that if you're modeling, either stick to a completely pre-tax cash flow assessment and don't model depreciation, or model, if you're modeling depreciation, you also have to do the post-tax analysis on the cash stream. So, sometimes the tax incentives of, what that might do is, here we have, the solar array being installed at $260 a watt, and then they're applying the tax credit, and then backing out the production of the array and the value of the production, and saying, okay, it's $1.82 after the tax credit, and you're saving this much money, so it's a 12-year payback. What a lot of solar installers will do when they're selling to businesses is they'll say, no, you get the tax credit plus the depreciation, and so for a residential, it would be a 12-year payback, but for you, it would be an 8-year payback. And that's not the correct way to do it. If you're modeling depreciation, you have to say, but you're also being taxed on the profit that you're making because you have a lower electric bill, because you're taking that series of payments. So we might have time at the end of the class to pull open Energy Toolbase and take a look at it. But what I have this video here that we can watch. But honestly, these graphics will be better. What Energy Toolbase does is basically the same thing that we did in Excel. You import the interval data for every single 15-minute period for your facility for the whole year, and then they add a solar array. And they're using the PV watts data. So, this is a sunny day, whereas on the right, it's a partly cloudy day. So it's the same data, PV watts, that you can get out of PV watts. They use an Energy Toolbase. But Energy Toolbase does this nice visuals, so you can better understand what's going on. If you're trying to fine tune your array size or your battery size, it's good to have a visual where you can kind of talk through and say, well, okay, on neither day did I hit my max peak, and so my solar array is taking care of this, and maybe what that means is I can downsize my solar array because I'm not really using it, and I'm not using the battery on these 2 days. Let's see. So they do it for, for instance, here's a visual where we can see this is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. The business or the school or whatever is not open. I didn't put any slides on this, but then they'll have an extra one for the battery. You add a battery here, and they'll say, okay, well, this is your load profile without the battery. And they'll say, okay, well, that means we got, if we turn the battery on at this point and do some load leveling, that means we got this much power, to charge the battery so that we have enough juice to do load leveling. So they have a battery model in here that will help you optimize the size of the battery. And then lastly, they do optimization algorithms, which you don't have to analyze too many variables. A big battery, a small battery, a big solar array, a small solar array, a large system or a small system. That's like 6 different, extremes that you have to look at. So it's not like you can't fiddle with this stuff, but what Energy Toolbase will do is tell you where to go look. Let's say in this case, they're saying, okay, a 29 kilowatt system, you're saving $200 a kilowatt, or a kilowatt. If you do a 57 kilowatt battery inverter, the effective value of the array remains true. You do an 86 kilowatt system and your effective generation rate is still pretty good, but then you go and do 114 kilowatt and all of a sudden you've shaved too much off your peak. Because, eventually you're going to have very spiky peaks, but the further down your slope that you go, the more you end up having to run that battery. And so eventually you get to a point of diminishing returns. And, while you can hone in on this on your own using the pencil and paper method, I think it's useful to know that there is software out there. And Energy Toolbase, I believe they offer a free trial, but you have to give them your credit card to get the free trial. So it's not the friendliest of free trials, but they do offer, a free trial for you to poke around with it. There's a YouTube video link if you, I guess you can't really click on it, but if you want to watch more, maybe we'll watch it at the end of class. Now, there are some other economic modelers out there, like PV Value and the System Advisor model. But PV Value is really only good at giving you like net present value analysis of solar production. It's not as intelligent as with storage. The System Advisor model is kind of a just like we just did in our spreadsheet. It's more of a hard-coded process to identifying demand management, whereas Energy Toolbase, when it's doing its models, it's actually going to look at, okay, on January 3rd, because I had this much battery usage, I maxed out my demand savings and my demand went all the way up to 80 kilowatts. If it recognizes that, then it won't run the battery in the model the rest of the month until the load gets up to 80 kilowatts. So if you had a target for 50 kilowatts, but your battery was too small and it ran it up to 80 kilowatts, it'll look ahead for the next few, for the rest of the month by readjusting that new target. So it has, a little bit more intelligent modeling than what you can do on your own. That said, that's why we spent so much time yesterday testing out different extrema, because that's really all they're doing is the same thing, but with equations rather than brute force. Okay, so let's say you have a facility, and that facility is open Monday through Friday and closed on weekends. And let's say it's you have a good base load here. This is a plateau. And so let's say this is what your load profile looks like. How would you go about developing this into a solar peaker plant? Well, first, you might want to go and just do a battery, that is just enough to shave off these peaks. this little spikiness here. A small system. Let's ignore the solar array for a moment. Let's just assume our load profile looked like this. You start out with a small system to shave off the spikiest of peaks. And that's going to be your quickest payback, and that's going to demonstrate, hey, y'all are pretty smart because everyone else is doing solar at a 20-year payback, and you're doing solar at a 6-year payback. That's great. What else do you have going for you? Then you say, okay, well, let's add a large solar array, pretty much enough to zero out the base load. So the first solar array you do is really small. Let me change my pen color here. The first solar array you do is really small, and it's only enough to charge, with your surplus solar production, and then shave off the morning peak, then get recharged by your solar array, and then shave off the evening peak. And so it needs to be just large enough to kind of shave off all of your extreme peaks. And of course, we're not really shaving off at this much, because we know we're going to have we might even be doing so small that we just shave off that much, just the spikiest of tips, because that's going to be a very cost-effective project. And it's not going to create too much, fuss either. Utility is not going to get mad at you for taking your peak demand and making it, relatively stable. They'll even though they'll lose your demand revenue, they still get some benefit from having a stabilized grid. And when you're looking at your optimization, you say, okay, well, how far down do I go before I'm actually running my battery all day rather than just shaving off the spikes? And that's a matter, that band right there is a matter of optimization. It's going to vary from one facility to the next. But the wider you go down into your base load, the longer your battery is going to run. And so the next step 2, is to add a big giant solar array. Maybe that is large enough to just hit your base load. So you don't have to worry about exporting things onto the grid. This could still be a zero export system. But really what they're doing with the size of this solar array is kind of ignoring the base load. If you have to sell back, electricity at 2 or 3 pennies a kilowatt hour to the utility, just give it to them. They can use the cheap electricity. You're going after other things. So what we're doing with this solar array is sizing it to take their kind of base load during their day, during their peak base load, and dragging it down to the night base load. So we're taking the kind of sustained daytime load and making a solar array large enough to get it down to the nighttime base time load. And I would even do it maybe a little bit more than that, because solar is relatively cheap nowadays. And what that's going to do is give you an effective load where now you have a morning peak and now you have an evening peak. And so at that point, you do another phase of batteries to yet again, chop the peak off. Because maybe that's a couple of years later and batteries have fallen more in price and it's time to do an expansion project. So kind of the last bit of it is to recognize that all this empty space that's left over from your solar array, but you're not above your new peak demand, all of this empty space represents the cheapest electricity in the United States. This is refined point of use electricity that is only costing the customer pennies a kilowatt hour. And so while this is sometimes a topic that goes in and out of style, I think it's worth mentioning that Bitcoin mining is a way to convert electricity into money. Bitcoin is a very, we don't get it in the United States because Bitcoin is a currency, and in the United States, the dollar, we're never going to need another currency. But in other countries where, Venezuela, their currency is not stable, and Bitcoin is more stable. As long as Bitcoin's an unstable currency, but as long as it's more stable than other countries' currencies, then it's a better currency for those other countries than their own. And so the way Bitcoin is supported is by computers donating their processing power to secure all the financial transactions associated with Bitcoin. And it takes a lot of computer processing power. It might not be a very environmental way to do things, so we're kind of putting the solar aside for a minute. So, if, at least we're doing large solar projects on top of our Bitcoin miners. But the only way you can make money off of Bitcoin mining is by having access to the very cheapest electricity out there in the world. And so you get a lot of Bitcoin mining going on in China and in other countries where industrial electricity is heavily subsidized to the point where someone can run a Bitcoin miner and make money off of it. And that's a terrible environmental policy. At the same time, it can be profitable at 3 or 4 cents a kilowatt hour. And if you have an extreme demand charge, you can have an energy rate of 3 or 4 cents a kilowatt hour. If you're outflowing onto the grid, you may only be paid 3 or 4 cents a kilowatt hour. If you can use energy during off-peak times, it only costs you 3 or 4 cents a kilowatt hour. And so, if you do your demand management as far as you can go in a cost-effective manner, the next way to make the project profitable is to Bitcoin mine during your off-peak times to get a little bit more profitability out of that job site. And then after you get to that point, the next phase of expansion would be to take the whole project off-grid entirely. And so, the reason why I mentioned that is it's not likely that, the project, if we're talking about taking every building in the United States off-grid, that's a discussion for, 50 years from now. It's not a discussion for today. But everything else in here, doing a solar peaker plant for maximum project profitability, and then, making additional money off of kicking it to the community solar for long-term project financing, and then seeing where else in the facility you can make additional money, like Bitcoin mining. Those are ways to go beyond just having a solar peaker and make more profitability off of that job. And so there's even evidences of Bitcoin mining. I found one. The Solar Alliance partners with blockchain for cryptocurrency development. It's in Murfreesboro, Illinois. Well, guess what? Murfreesboro, Illinois is right here. It's right where they're at their cheapest energy rate and highest demand rate. It's no coincidence that a Bitcoin mining facility is being developed at that point.